Hello, everyone. Welcome to the lesson on principles and applications of mechatronic systems. I'm the lecturer, Leon Guangrue. Today we look at Chapter 4, Servo Control Technology, 3 Control Methods of Servo Motor. First, let's look at the learning objectives of this lesson. We aim to gain in-depth understanding of the 3 closed-loop control system of AC synchronous servo motor, including the hierarchical structure, working principle and interrelationship of current loop, speed loop, and position loop, and master the bandwidth setting principles and debugging sequence of each loop. Be proficient in the definitions, principles, closed-loop structure usage, and typical application scenarios of torque control, speed control, and position control. And be able to select appropriate control methods according to different scenarios and understand the logic behind them. Now, let's start the learning of 3 control methods of servo motor. There are 3 main control methods of servo motor: torque control, speed control, and position control. These control methods are based on the 3 closed-loop control structure of servo motor. In principle, the FOC closed-loop control mentioned before realizes the closed-loop control of motor torque, because IQ ref corresponds to the torque magnitude, and controlling IQ ref is controlling the torque. Based on this, when we add speed loop and position loop, a 3 closed-loop control strategy of servo drive is formed, thus realizing a high-performance AC servo system. The 3 closed-loop system is a hierarchical system nested step by step, which is current loop, torque loop, speed loop, and position loop. The normal operation of the inner ring is the basis for the effective setting value of the outer ring, and the principle of setting from the inside to the outside and ring by ring should be followed during debugging. Let's talk about the current loop first. The current loop is the innermost loop, which controls the DQ axis current of the stator winding to realize the decoupling of torque and magnetic field, and has a bandwidth of 500 Hz to 3 kHz. The speed loop bandwidth is 50 Hz to 200 Hz, and the ratio of 5:1 to 10:1 is maintained with the current loop bandwidth. The position loop bandwidth is generally 10 Hz to 50 Hz. High-precision models, such as Inovant's SV660 series, can be increased to more than 50 Hz through feed-forward control to achieve micron-level positioning. The control effect of servo motor is mainly affected by the controlled object and PID parameters, and the inertia ratio and 3-loop PID parameters are extremely important. The manufacturer usually does not open the current loop parameters. Users can set the gain and integration time of the speed loop and position loop. Usually, the differential term D is rarely used or not used. Stiffness is the key concept of servo control system. The greater the stiffness value, the faster the system responds, the stronger the anti-disturbance and stability. For example, the stiffness value of Inovant's SV630 series servo motor is divided into 0 to 41, and 41 indicates the greatest stiffness. High stiffness value, level 18 to 41, brings great speed loop gain and fast system response, but it may cause mechanical resonance or overshoot, which is suitable for high-precision stiffness connection scenarios. Low stiffness value, level 0 to 12, brings lower speed loop gain, stable system, but delaying response, and it is suitable for low stiffness or vibration-sensitive mechanisms. For every 5-level increase in stiffness, the bandwidth of the speed loop increases by about 20%, and the system becomes more sensitive to sudden load changes. Generally, the rigidity value can be directly set for quick debugging or low accuracy requirements, and the PID parameters need to be manually adjusted for high precision or special loads. Next, Let's take a look at these three control methods respectively. First is torque control method. Torque control sets the motor output torque through external analog signal, PWM frequency, or duty cycle, and is controlled only by current loop. The rotation state of the motor is closely related to the load. The load is lower than the set torque, and the motor accelerates. The load is equal to the torque, and the motor is at a constant speed. When the load is higher than the torque, the motor decelerates or reverses. For example, the motor may reverse when a heavy object is lowered. Key applications of torque control in industrial occasions. In precision winding and unwinding equipment, materials with different wire diameters require different torques. Thin wires need low torque to prevent breakage, and thick wires need high torque to ensure tightness. According to torque equals force times radius, the torque needs to be dynamically adjusted to offset the torque change caused by the radius change during winding. For example, optical fiber drawing requires extremely high precision torque control to prevent brittle fracture. In aluminum foil, unwinding also requires stable torque to ensure smoothness and wrinkle prevention. This dynamic compensation mechanism ensures material processing integrity and product yield. Second is speed control method. Speed control realizes precise control of motor speed through analog input or pulse frequency. The larger the input signal or the higher the pulse frequency, the faster the motor speed, and vice versa. This method uses current loop and speed loop control. Speed control technology is crucial in RPM-sensitive scenarios. Industrial conveyor wires require constant speed to ensure accuracy and smoothness. The textile field requires differentiated speed regulation. Fine knitting requires a low speed, and high-speed process pursues efficiency. The intelligent speed regulation system can accurately regulate the motor speed to meet different production needs, and its dynamic speed regulation capability has become the core technical element of modern intelligent manufacturing. Third is position control method. The position control method uses all three closed-loop structures, which can strictly control the motor speed and position to achieve precise positioning. It is common in scenarios such as CNC machine tools and printing machinery. The motor speed is determined by the pulse frequency, and the rotation angle is determined by the number of pulses. For example, when processing with CNC machine tools, by controlling the frequency and quantity of pulses, high-precision machining can be achieved to ensure the dimensional accuracy and surface quality of parts. In addition, in order to meet different control needs, some servo motors support direct assignment of speed and position settings through communication, breaking the limitations of traditional pulse control and making them more flexible and convenient. The user sets the value through the communication interface, and the motor quickly responds and performs actions to adapt to complex control scenarios. This lesson provides an in-depth explanation of the three closed-loop control principle and three control methods of AC synchronous servo motors. The three closed-loop control system is a current loop, torque loop, a speed loop, and a position loop from the inside to the outside. The levels are nested, and there are clear principles for debugging. Characteristics and applications of the three control methods. Torque control only uses current loops, which suit for the strict material stressing scenarios. The first two loops are used for speed control, which is suitable for scenarios with strict speed requirements. Position control uses all closed-loop structures and is often used in scenarios that require precise positioning, such as CNC machine tools and printing machinery. Some servo motors also support flexible speed setting and positioning through communication. That concludes this lesson. Thank you for listening. See you next time.